Can you hear me? Yeah. Okay. So anyway, so that's the neuroprosthesis system that some of you might have heard of already. And then the other way in which you can reduce cost pains, for example, with somebody who's visually blind, is to use something called cortical prosthesis. And this is already an idea that was introduced back in the 70s by William Bedell. And there's a really nice paper in the Journal of Physiology in 1974 where he published work about how prostheses can be produced by electrical stimulation of human occipital cortex and the application to development of prostheses of the blind. So this is really something that's been going on for a while, and this is one of his most famous patients, and he had his prostheses for supposedly over 20 years, and could do things like driving a car and so on. So the technology really hasn't, the way of reducing prostheses really hasn't changed so much, as you will see. But what really has happened is that there has been huge progress in different types of technology to make this prosthesis even better. Right? And so one of them is the progress in probe technology. So you might have heard about the Utah electrode array with 96 electrodes, and this is the one that is FDA approved, that is used in different labs for experiments either in mice, rats, and actually also in humans nowadays. And then there's also Neuropixels. So this is something that you can buy actually through a website, neuropixels.org. And you can see that instead of 96 electrodes, you can have actually over 1,000 recording sites. It's on a shank that's very long and skinny, and it has 384 parallel configurable recording channels integrated in the base. And so the electrodes are seen right here at the end. And this is a sort of a blow up for this my mouse system. You guys don't see my mouse? Yeah. Okay. Right. And so this is the blow up, and you can see the recording sites of the frequency pixelated pattern. And each of these recording sites are extremely small and structured. Right. So you can see that the technology has hugely improved. And then coupled with that is this huge progress in transistor technology, because also the sizes of transistors are very small over the years. And so, for example, this is 10 nanometer technology. Going down nowadays, you can even get to 3 nanometer technology. And so, which means that you can actually miniaturize all these electronic circuits for recording or simulation to something that's very small. And so that way you can also support probe technology that you can develop on more than 1,000 probes. And so the other big thing that happened, of course, is deep learning. So you'll learn about this. And so you can have nowadays train easily at convolution level, for example, to take images coming in, and then you can classify them as a lion or etc. And so we're hoping that with this different technology developments is that you could go to something that looks like this. So this is a cartoon of something we're imagining at the start of this project I'm going to talk about. And the idea is that you can have a camera that would send images to a visual processing unit in some wireless way, and then take the output and then drive an implant in the visual cortex. And then even use recordings from this implant to affect how you should stimulate the electrodes. And so what I'm going to do now is talk a bit about the consortium itself, and then to present some of the work that you're doing, not my work, right, so that you can have an idea of what the state of the art is, at least for our consortium. And then I'll talk, on the second half of the talk, I'll talk about some of the work that we're doing within this project. So here's the consortium. It consists of 7 to 8 partners. So I'm the coordinator of this project. It involves 2 groups doing experiments, Peter Waltiner from Cornell and also Eduardo Fernandez from UNH in Spain. And actually this picture was taken just after our second review meeting. And so this is somewhat at the end of the third year now. And we also have a partner from SKU, Marcel Derwin, who does a lot of AI algorithms, and Carolina Lopez from IMEC, and we're the ones who develop the circuits also for neuroprobes, we saw earlier. And I am Ted Petrobuda, who developed also the probe technology for neuroprobes in the past. then also Maria Axley is also developing core technology. And also we have a small startup for the students. And so, so I think it's a really nice group in the sense that we have different people doing different parts of this entire system. And so this, I'm going to show you kind of the different pieces. It looks a little bit busy, but you can see how the partners are all involved in some way. And so the SKU group develops these algorithms that take camera images coming in, and then we train a screen crystal generation network that produces the stimulation patterns that will then drive this IMEC chip that has a high channel count with stimulation electronics. And us at the University of Zurich, what we're supposed to do is to take this network and implement them on some sort of hardware, so it's the power, hardware, social, and then you should produce them the actual simulation pulses to the IMEC chip. And then the output of the IMEC chip is used to drive this core technology, right, that's developed by the group at INC-IEM, and the group at Canal will then test these codes in mice, primates. Hopefully we'll see nice screen patterns of the person. And then the group at UMH is also doing experiments to test the codes. And also at the same time, you'll see later on, I'll show a video, we actually have been doing experiments with the Utah electrodes because those are FDA approved and we can implant them in different subjects to see how we should control the stimulation of this electrode so that the person can actually see something that's useful. Okay, so in short, so the goal of this project is to construct a neuroprosthesis for restoration of sight. Hopefully we'll reach over 1,000 flexible multi-electrode arrays to stimulation and recording sites. And I see that has both stimulation and recording channels. And on the other side is to also create adaptive machine learning algorithms for a new kind of brain-computer interfacing technology. And so this consists of the two parts that I just mentioned, the plasma stimulation network connected to the camera, and then the real-time part of the system that runs the network and interface also to the stimulation recording I see in the future. Now, so now I'm going to go on and talk about the latest progress in the codes that have been developed at INTech and also electronics. This the PIs are Maria Axley and Patrick Luder, along with Christian Doller. You can see now this microelectrode arrays look like this. So there's 4 shanks, where instead of simulation and recording sites, one is shank. And these are flexible electrodes. And they have this material, usually if you see flexible electrodes, it's usually polyimide, connection lines are platinum, and then they produce a combination of iridium oxide and also piezo electrodes. And so you can see now, if you look at the SEM picture, you can see now this different sites, right? And if you go up now to the scale, you can see it's a little rectangular thing. If you go up even more to something that's less than a few micron, you can see it looks a little bit like worms, I think. Yeah. Anyway, you can find details on this in this paper, which we just put out last year. So these lectures are kind of micro scale, and something we're concerned about is compressibility, is how good are these recording sites or simulation sites, particularly when you're using for a very long time. Are they going to degrade in some way? And anyway, this picture here shows you how flexible these electrodes are, but you can see they're kind of wrapped around the volume, and the scale here is about 100 micron. Right, and then the way, because this is the most challenging part, is how do you insert these flexible electrodes into the cortex, right? Because they're not stiff anymore, right? The neural pixels are silicon coated, so they stick, so it's easier to insert into the brain, but not with this flexible codes. And so what they do is they design something which they call a silicon shuttle. I don't know if you guys can see it, but here on this PCB, they actually have a silicon shank coming out here, and then the polyimide coats are actually sitting on top of that. I don't know if you guys can see it. And then you can see also the cable that comes out from this polyimide coats. And hopefully you can see the video. So I can more of this. You see how, so basically the video shows how to insert the probes to take away the shovel, and then then they remove everything, right? And then you can see the cables sticking out. Ready to play the game, so it's really hard to see it because it's so transparent. Also, it's very hard to catch it. So when you insert the whole thing in, remember this is with the shovel, it's open, so you can put the whole thing in. But then somehow you have to ensure that the plates stay inside, right? The smaller thing, yeah, I think it's made of clay, but with a similar kind of consistency as what the tissue would be. Yeah, and this has now been tested in mice and stuff. Because if you don't do it right, then basically the whole thing comes down again. Right? So making sure that it goes in and the space there is like quite tricky. And so this is the part that I think other groups are building this kind of flexible codes are also trying to figure out solutions. And they can not easily, you can set the codes and ensure that they stay there. Going to pull out the camera for the shovel. Okay, and then you can have like an interconnection board that goes kind of the whole thing, and then you can put other kinds of chips on it, like INC basic, for example, this base code. Okay, so now here's the video thing. Okay, so next thing I want to show, going back to my laser pointer, is the study that we've done to ensure that the sports don't degrade over time. And so what you see here is a micrograph of the probe going into the cortex, and this is in a mouse. And what we want to see is that the cells stay healthy after a while. And so this is after 55 weeks of stimulation. So you stick the probes in, you stimulate for 55 weeks, and you want to be sure that the cells don't die around the probes, right? So basically you want to get areas that don't go black. That if the cells are dying away. And so we also want to look at the probes to make sure that the material hasn't degraded, and this is what we're trying to show here is that if you look at single shank, and then if you look at one of the stimulation cells, then you can see that it looks pretty good still, like after this 55 weeks of continuous stimulation. And here are even more measurements that we usually do with probes. So again, this is from a mouse. And
Yes.
Yeah. Well, right here doesn't. Yeah. It's not.
That's good.
There's no feedback. Can they hear you? I mean, do you see a chat that tells you? Wait, how do you know? Oh, I see the mic going. Oh, much better right now. Okay, now I see the chat. So everything's good now to go? That's good. Okay, so let me continue then. Yeah. So basically you stimulate with a, oh, right, yes. You're thinking you can see my mouse pointer. Okay, so you stimulate with pulses, so up to 8 billion pulses with amplitudes of 18 microamps or 25 microamps. And then you look at the voltage drop as you stimulate more and more of these pulses. And pretty much, I think it doesn't change so much, right? It still stays about even around 2 to 3 millivolts. And the other thing that usually people do when they fabricate electrodes is they do this measurement of impedance versus frequency, right? And they look at what the impedance is around 100 hertz. And so in this case, what the group was concerned with is when you take the original electrode, the initial one, and then you do these measurements, and then now you do it with electrodes that are unpulsed or they're pulsed at 18 or 25 microamps, you want to see whether this curve changes or not. And so what they show here is that the curve doesn't change at all. So it means that the electrodes are quite stable. And the last thing here is to show what happens or what's the stimulation amplitude that you need to induce a percept. And so if you look at how it changes over weeks, so this is up to 55 weeks, you can see you need about 2 to 4 microamps, and there's a slight change towards 6 microamps or so after 55 weeks. So that's about a year or so. It's pretty good. Yeah.
How do you select the train of the pulses?
How do you select the train of the pulses?
Yeah.
Yeah, so as I understand is they use something, this pattern that looks like this, right? And then they keep on stimulating it at 100 hertz. Is that what you mean?
Yeah, but any array specific or all the in all the
Oh, you mean like at different rates or something
Yeah.
like that? No, I think it's fixed to these numbers that you see here. Yeah, and then it's really what I think they're more interested, at least for these measurements, is the pulses, the number of pulses that you give.
Yeah, because I was thinking about the saturation of the neurons. Because it's continually.
Yeah.
and there is something-
Yeah, right. If you stimulate, I understand what you're saying. Yeah. If you stimulate frequently, you're going to saturate. Yeah, yeah. No, I think they allow enough time so that the charge doesn't accumulate. Yeah, and also you're doing this negative and then positive, so the charge is this charge balancing going on, right? So you don't get that charge. Yeah.
And then something specific array pattern, because you know that
This.
if you feed completely at the same time,
Yeah.
there probably is a crosstalk between.
Yes. Yeah. All those things we have to worry about. Yeah. I think this is just with a single electrode and then just hitting that one side. Yeah. And then of course the other stuff is the crossfire. They're doing all those measurements right now to be sure, at least to understand the amount of crossfire you could get across the recording sites or the simulation sites also. Yeah. It's definitely something to think about when you're building this large multi-array electrodes. Is that it's nice to have all these electrodes, but then you have to worry about crosstalk, accumulation of charge, etc. Yeah. Yes.
Does injecting electrons affect the pH or the oxidation state? Can you repeat the question?
Yes, I think the injection of electrons affect the pH or the oxidation state. It's a very good question. I don't have the answer. I don't think we ever asked this question, but probably the group doing this experiments knows the answer. I can ask them. Yeah. And what I show here is a comparison table of some specs that, if you're interested in this kind of electrodes, is the specs that usually they measure, like the thickness of the electrode, the number of electrodes that you can have along a shank or probe, the number of shanks. In this case, just one, but eventually we would have 4. And then right now for at least for this paper, they reported 32 electrodes, but we're going to head towards something much higher, 256. And then this thing that I talked about, the impedance versus frequency. So if you look just across these 3 papers, so they have something that's quite low. It's only 33 kilo ohms at 1 hertz. 1 kilohertz. So yeah, so they have a pretty low impedance, and that's kind of important when you have electrodes, right? Because you want to use very little current to induce a change in the voltage. Yeah, so low impedance is good. Yeah, and also the electrode dimension. There's some other numbers here, and so if you're interested, check out this paper if you're working in this area, so that you have an idea of their technology. Okay, so the next thing that I'm actually going to show now, which I actually find very exciting, because really this is putting this ultra-array electrodes into humans, and there were some experiments that one of our partners did, Eduardo Fernandez, at University of Miguel Hernandez in Spain. And so this is the very first patient that received this implant. And with the regulations, you can only implant the person with these electrodes for 6 months, and then you have to remove them. Yeah. And so they published a paper in the Journal of Clinical Investigation where they describe all the outcome and the different experiments that they did with the person. So here you can see she looks happy. These are some of the signals that were recorded from the electrodes. And so I'm going to show you next is a video where she's going to point at the border between this black and white stripes. Okay, just using the implant. Okay, see this would, oh yeah, I have to come out the pointer again. There's some dialogue in Spanish, but I don't know if you'll get the audio.
Understand on that, right?
Yeah, but I mean,
Ahí, sí, sí, sí. Ahí, sí, sí. Ahí estás en la de la línea.
Ahí aparece. Es luminoso, ¿eh? No. Bueno, es negro y blanco por dentro.
El negro y blanco por dentro, efectivamente.
okay. So yeah, so I mean, this is really something. So for every patient, I think they only have 3 or 4 so far, and for every patient, they really work with them like almost the whole day, every day for 6 months. So we really work with the person to help them see the phosphines or to understand what is it that they're seeing with the phosphines, right? So they know how to stimulate the electrodes so that the person actually can see, for example, here the border. And this, I think the next one that I'm showing is the second patient that they had. And so you can see how it sits on top of the skull. Right? In this case, actually the electrodes went into V2 instead of V1. So the first one, you went into V1. The second one, they had to move it to V2 because of the shape of the head. And as I understand, because the person, when you slept, the thing would hit. Because when you sleep, you don't want this thing to like smack onto the mattress and stuff. Yeah, and so at this UMH Institute, they also have a virtual reality room, right? And so what you see here is the screen. On the screen here, it's showing so these obstacles and the person's holding on to these bars, right? And then when they walk, the floor basically moves, so they have a sense of how that person's walking, and then they change the picture accordingly. And so here the subject is trying to play a game where he has to avoid hitting these obstacles and walk down to the end of the corridor. You see that it's trying to go to the right. Actually, I was in this room and you put on this goggles, but so basically the floor moves and it's very you feel very funny, right? In fact, when Toby tried it, he walked right into the screen. And so they give you this kind of thing that you can hang on to so that you don't suddenly fall off somewhere or hit something. Yeah. So anyway, you can see that this putting implants in humans is possible. You can get them to do very simple tasks like detecting lines and avoiding corridors. Or they also have a video where they show that the person actually could find a smartphone right in the room. So I think it is getting there, but you really need to have a lot of electrodes to get an idea of like a picture, because remember, this is 96 electrodes, right? 96, which imagine how small that picture is, right? So what we see is not what they're going to see. So you have to give them information within this very small size of an image, if you like. Okay, so now I'm going on to the stuff that our group did within this project. Okay, still good. So actually there's 3 parts. I mean, they're very short. for each of them, but it's just to give you an idea of the development within this area. And in the first part here, I'll talk about the 128 channel real-time visual deep stimulation system and hardware, which involves the phosphine generation network, the implementation onto currently an FPGA instead of ASIC as yet, and then interface to the IMEC stimulation chip. And then the second part is some work that we did at the very beginning to see how well we can do decoding of primate visual cortical recordings using deep networks, right? And the third part is a demonstrator of the portable phosphine system. In this case, we didn't use a camera, we used the DVS, right? Because the DVS gives you a sparse output in some conditions. So it could be useful. Okay, so for this first part over here, so this again involves partners from different institutions, Radboud and IMEC. And so again, the idea here is that a person will be looking at an image, in this case, a letter M, and then the frames from the camera will go to, let me put on my pointer again, into this system, which we call VPDNN. It stands for Visual Prosthesis Deep Neural Network System. And then the output would then, the stimulation currents would then drive the implant in the visual cortex. And hopefully the person would see something that looks like this, a phosphine pattern that sort of resembles the M. And in this VPDNN, there are two pieces. So the first part is the accelerator that we built to implement the phosphine generation network. And then to the SPI interface, we send the information across to the stimulation ASIC. And so what you hear about next is that I'm going to just briefly describe what we call the end-to-end phosphine stimulation network receiving the input frames, and then show you a couple of videos that show you the real-time system running the network and also interface to the ASIC with the stimulation channels. Now, so how can you produce phosphine maps from the input image? And so remember also that the array of electrodes is quite small, right? So you can take the raw image intensity and then map it directly to phosphines, and it's going to look something like this, something very busy, noisy. It's very difficult to see anything, right? So this is just like a simulated picture of what the person would see. Okay. So to make it sparser, you could run like a canny edge detector, and then just look for edges. And so then now the phosphine map is a lot sparser, so it's more helpful, but still very difficult to say that there's a person here, and then there's a train here, etc. So there's another output that you could use, and this is called a semantic edge detection algorithm, where what you do is you only show edges of certain classes, right? So for example, if I'm only interested in people, then I show edges only of the people, and then I transfer them, of course, into the corresponding phosphine map. And now you can see this output is more meaningful, and you can use it better if you're trying to navigate through a city. Okay, so yet another way that you could create this phosphine output was this work done at Radboud with the phosphine stimulation network. And so the model really is what we call a variational autoencoder. So it consists of two pieces, an encoder and a decoder part, right? The encoder receives the input image, right? It maps it down to a much smaller latent space. So in this case, it's a 32 by 32 array. So matching what you would get with the electrodes. And then when you train it, right? So basically you train it so that the decoder produces an output that is as close as possible to the input. And so with this 32 by 32 output, you first pass it through a phosphine simulator. So the idea is to have an idea of what the phosphines or the size of the phosphines would look like, right? Depending on where you put the electrodes. And you would then get a phosphine map that looks like this. In this case, it was scaled up to 256 squared. And the map is what they call a synthetic prosthetic vision map. And then now you feed this to the decoder, which produces the reconstructed input image. You train it so that you reduce the differences between these two images, and plus you include an additional loss during training to produce very sparse latent maps. Okay. And then in the results that come later, we use a data set that came from the group, and it basically consists of letters from the alphabet displayed in one of 47 font types. And we use 38 of them for the training data set and 9 font types for the validation data set. Now, the nice thing about this autoencoder is that this part over here is only used during training, right? And so if I'm now going to implement the network on an ASIC or an FPGA, I can basically throw all this away. And all I need is to implement an encoder. So what we had to do was to take the network from Raboot, and we did some modifications because we're going to hardware. So we cannot just take any architecture and then map it down to hardware easily. So in this case, they were using a CNN network, but we retrained the network so that, for hardware reasons, so that it would use only rectified linear units for the activation function. The weights are only 8 bits, so 8-bit parameters. And also in the original network, they had skip connections, and we didn't want to have a network with skip connections because on hardware it's actually quite expensive because you have to get extra memory, and then if you're doing the hardware stuff, you know that this is not something that's easy. And so we replaced it with an extra convolution layer to get the accuracy, the same accuracy that they got on that alphabet data set. In total, you can see it's not a very big network. It's about 94,000 parameters. Right? And just to give you an idea of what the inputs and reconstructed outputs look like. So here are 5 examples of the alphabet. This is the phosphine map, right? And since we had trained it with 8-bit parameters, so what I'm showing here is what you would get if you use FP32, floating point 32 bits, or int8, right? And you can see it's not so different between the 2 maps. And then the reconstructed output for the FP32 looks very similar to the input. And if you look at the reconstructed outputs for the int8, it also looks very similar. So basically you can get away with quantized parameters for your weights, right? So it's good for us. And finally, we implemented this network, which we call it a VPDNN accelerator. We implemented on the Zybo Z7 FPGA board. And so you can see the FPGA board over here. Yeah, the accelerator runs on the 100 megahertz clock frequency, so quite low frequency, uses 48 multipliers, 16 processing elements per array, parameters quantized to 8 bits, and then we do zero skipping, which we also call null hop, and basically for energy efficiency, we skip over any activations that are 0 to speed up computation. And so in this picture over here, you can see the camera interface to the FPGA board. And then the output of the network basically is displayed on this monitor. And what you see here are 2 little letters. You're going to see a video. So you're going to see the input to the camera. So this is the letter. And then the output of the network is much smaller, right? Because we're going from a 128 by 28 image down to 32 by 32. So you see it's very tiny. And just by chance, so that you guys don't think it's just downscaling the input, is that this network somehow managed to learn just a downscale input of a downscale version of the input. It just looks like that, but with images, it doesn't look like that. Yeah. And then for those of you who might be interested in what the zero skipping idea is about, is that when we send a feature map from one of the convolution layers, and here's an example where you have a lot of zeros, and then maybe 2 pixels where you have a non-zero value. Then we create actually an additional map called the sparsity map. And we put an index only on those pixels that have a non-zero value. So you see a 1 here and a 1 here. So sending the sparsity map across is much cheaper than sending kind of a map with analog values. And then we send across just the 2 values of the 2 pixels and non-zero. So it's a lot cheaper, yeah. And this is called zero skipping. Okay, here's the video with the camera attached to the FPGA board. I have to come out of this thing. Okay, it's gonna look at the letters on that piece of paper, and here you can see the input, right? The different letters, and here's the output. So it's very, I don't think I can show, maybe I can. Yeah, you can see the output of the network. So it's something very tiny over here. Yeah. Okay. And then we also did some comparison to another platform, embedded platform called the Jetson Nano. And so we compared in terms of the precision, latency, frames per second, and also the delta incremental power that you get. And I guess if you look across all this, I think what you see is that with the VPDNN with INT-8, so let's just look at the first and third rows. So the latency is about 12 milliseconds, which is within the specs that we would like to have. Basically, just by running the network, you can go about 83 frames per second. The Jetson Nano can do something much better, but the difference is in the incremental power that you get with the FPGA platform versus the Jetson Nano. So if we're going for power, then the FPGA accelerator will be much better. And of course, then if you know what the network is that you would like to use, then you can go down to an ASIC and save even more power. Right? That's the next step. Now the other piece of it is the Cortical stimulation recording ASIC from IMAC, and I think I would just briefly touch on this. It came out in a paper at ETH, and it has 8 stimulation units. So basically, they can store 8 different stimulation patterns. It's got 128 output stages, so you can stimulate 128 sites, and it has 64 recording channels. And here you can see the different blocks on the ASIC. It's placed on this little PCB here. And then you can stack them up if you want. So that if you want to have more channels, so in this case, if you stack 4 of them, you can get 512 channels, simulation channels, and then connect it to what they call a head stage, right? So it's the thing that you put on top of the skull. And then to control the head stage, they have this box over here with a very thin cable, right, that they actually custom made to drive the head stage. I'm going to skip over the specs and show you the video of this running if I switch. And so in this case, this was actually an early experiment that we did before we had the camera going. And so the letters or alphabet letters are fed into the FPGA. And so here's the VPDNN, here's their box, the NeuroViper box they call it. And here's an LED display to show what the stimulation output would have looked like, right? So ideally, you can see on here, here's the input, here's the output of the phosphine network. Oh, right, okay. The input, the output of phosphine network, and also then the stimulation output, right? Which should look like the little P that you see here. And so here you see, yeah, that it's the same. So basically it tells us that everything is working, right? And so we're ready to interface now with the probes. Okay, so now the second part here, what we did was, remember it's a closed loop system. So we're also interested in the decoding that we could get from the recordings, right? Not from the stimulation, but the recordings. Because you stimulate somewhere and then you could look at the recordings in the same area and see what has happened, right? And because we, oh yeah.
Just one question, just out of curiosity. So for the actual stimulation, do you rely on like retinotropy somehow, or do you think that
No.
you put in the electrodes there and somehow the neurons will reconfigure to kind of make sense of the process?
Yeah, so it depends on where you put the electrodes, and you can look at the cortical map and know what the magnification is where you implanted the electrodes. And then with the phosphine simulator that Jonas or Rabut did, you can actually map it to where the electrodes will be sitting. So to make it more realistic, because you could have the same electrode put out the same current, and it could look like a little phosphine dot, right? Or it could look like a big phosphine dot, right? So they have all this, they have a software that tells you what you would see.
But ultimately, you want to get the first piece mapped on some regional topic map, or is it kind of, do you expect the circuit to just rewire like the visual cortex?
No, I think I mean, what you would like, I guess when you see the person doing the thing with the edges, it should look like a regional topic map or some type or some image. But because the array is so small, you can imagine that you don't have to do that all the time. So if I tell you look for a smartphone, just an example, it's very difficult to show the edge of the smartphone, right? Because it's such a small field of view. So instead, you could just show a dot. Just imagine you have the whole image here, and I just show you a dot of where the phone would be.
Because there's a network that's processing that image.
Yeah.
Exactly.
Right. So you just want to give information to the person, right? Because they just see these bright dots, and where they see them depends on which electrode you stimulate. And so you could give them like a code, right? What does dots mean also? Yeah. So anyway, for the second part here, so this is the neurodecoding that we did on the set of recordings from the primate visual cortex. It's done by two of the students in the group. And so the idea here is whether we can do fast temporal decoding of recorded responses from V1 to V4 cortical areas of the primate using deep learning. And then whether we can actually reduce the computational resource by decoding only from a subset of 1024 electrodes. Because in this recording data set, you see that I'm going to pass the state-of-art work. So this is the data set that we got from Jing Chen and Peter Rolfsamer over at NIN, and it was from a Nature paper published in 2020, where they had 16 Utah arrays implanted in a V1 and V4 of the primary visual cortex. And so the experiments here were done where the macaque performed a visual discrimination task. So again, there was 1,024 electrodes, 896 implanted in V1 and 128 in V4, over close to 3,000 trials, 2780, and each trial is 1,500 milliseconds long. And so they have this thing, what they call a set of familiar letters, one semi-familiar letter or semi-novel letter, and then a totally novel symbol. And instead of presenting just like the A, as you see here, they actually try to match what the percept might be if you could simulate illicit phosphenes, right? And so basically they make like a pixelated picture of the A. Right?
The hypothesis in this case is that you suppose that the image is projected over the cortex directly?
It's projected so that it's like you're looking at the scene, and then you see the letter.
The projection is directly over the neurons on the cortex.
In the cortex. So yeah, the electrodes are sitting in the cortex.
Possible can have all the different array.
Yeah, so they have to do some form of calibration to know that when I stimulate this electrode here, where would the percept be? Yeah. So it's quite a bit, some work that you need to do, to map it out. Probably that's related to your question. Yeah, and so shortly you present, so you fix it on this red dot over here, and then you present the letter usually on the lower right, as you see here. And then the monkey would then, after some time of the stimulus presentation, would saccade to one of 4 positions to tell you which letter it thought it saw. Okay. And if you look at an example recording from one of the channels, then this is over 1,500 milliseconds, right? You see the pre-stimulus phase where the monkey is just looking at a fixation point. Then you present the stimulus, you see that it's a peak, then it goes to some level, goes down to some level. And then you take away the stimulus, and then you see there's a rebound. You see yet another peak for some of the stimulus letters, and then it goes down again, right? And so there's different curves here correspond to the different letters or symbols. Yeah. And so we have a lot of this, and so we're trying to see if a deep network can be trained so that if I give you these recordings, then can I tell which letter I was stimulating the animal with? Okay. I'm going to skip over this slide. It's a bit heavy, but one thing is that we wanted to see whether you can use small size window in order to discriminate the letter. And so what I'm showing here quickly, in the end, we use the convolutional neural network, right? And this is a running window, and we choose different size windows from the different recording areas. So for example, the solid lines here always come from electrodes in V1, and different size windows going from 300 milliseconds down to 20 milliseconds. And also the dotted ones here come from V4, again for different time windows. And then this is the performance of the monkey. This is random guessing. So if you do anything better than this, it's good. Right? and anyway, so now you can see quickly that you get the highest accuracy probably in like 100 milliseconds or so right after stimulus onset. You can, for these different solid line curves, you can see actually it's quite good, right? It's over 80%, even using a small window, running window. And interestingly, between V1 and V4, you can see that you get better accuracy if you use the recordings in V1 versus the ones in V4. Okay. It was just something we observed, right? As to why this is so, I mean, you can always make some hypothesis, right? Because V4 is a higher area and it's looking for something else. Yeah. And then the other thing that we wanted to check out is if I have the 1024 electrodes, it's not great if I want to have, low latency for the network. So maybe not all the electrodes are needed, right? So can we now do electrode selection, right? And so it happens in the data set, we have the spatial location of each electrode and the size of the receptive field. And so in the V1 recording areas, this picture here shows with all the little dots, it shows you where the electrodes are in relation to the letter that's being projected, and also in V4. And so the short answer is by training a network that uses another component, which is called the squeeze and excitation network. I don't know if you guys have heard of it, but basically you can train this network to look for the importance of each of the channels, of 1024 channels. And then you can look at the accuracy using only a subset of the channels. So in this case, we went from 256 channels out of the 1024 down to one channel. And we looked at what the accuracy, how the accuracy would drop as you drop down the number of electrodes. And this is ranked by importance, which is something you got from this network, the squeeze and excitation network. And you see, even if I go down to 120 electrodes, the accuracy didn't drop so much, right? This is the red curve, right? Then it drops more and more as you throw away more electrodes. And then this is another method that we use to decide on the number of electrodes you want to use. And so we did like a threshold on the amplitude of the recordings. And so basically we took all the electrodes that have recording amplitudes above 0.2 and also 0.1, 0.01. I think we ended up here with about 700 electrodes and here 400 electrodes and here about 700 electrodes. And then we just did random selection of this subset, right? So that, and then we use it for looking at what the accuracy would be. Again, it's worse than if you had learned what the important channels are. Right? So the accuracy dropped much faster. And so you can go back and look and say, let me take the 10 most important channels, right, from the squeeze and excitation network. And you can see that the receptive fields basically lie on top of the stimulus, right? So it seems that it's correct that you should choose those channels. And then if you choose the 10 least important channels, you can see that it actually sits outside the stimulus. So you can see a number of them sitting outside the stimulus area. Now, the last part here is about the demonstrator of a portable phosphine system with a DVS camera. I'm going to jump over this, assume everybody knows the DVS. And so this videos here show you why you want to use a DVS. And so again, if I have the image here, you can see somebody goes through. If I do an edge detection, then I might get this very noisy output, which is not great for creating a phosphine map. But with a DVS, you can see it's very sparse. There's nothing, right? And then only when somebody walks through or bikes through, then suddenly you see some output, like right here. Yeah, you see now you can see the bicycles going across. So it seems great for for its prosthetic vision. And the same thing here. Oop, let me play. Yeah, the hand waving thing. So in this case, yeah, the DVS and the edge output looks quite similar. Okay, so what you could do is with the Davis, remember it puts up both frames and also the DVS events. So you can now process the two different outputs of the Davis, right? So you can take the frames, look for edges, and then create a phosphene map from that. Or you can directly use the DVS events, do some noise filtering, right, to get rid of noise events, and then create a phosphene map from there. And then send both pictures onto a VR headset so you can see what the differences are. Right, and to do the phosphene generation, basically you would take either the edge filter or the DVS event output, do some bit of smoothing, decide where the electrodes are, and so then you do the proper convolution, Gaussian convolution, so that you can get the actual phosphene dot size where the electrodes are sitting. And so we built our own demonstrator for an event called Scientifica. So this was done by Nicholas Tan in the group. And so here you can see the Davis hooked up to a VR display. And we ran the phosphene simulator on the Jetson Orin. It's a 10-watt system, and we can run the whole thing at about 20 to 35 frames per second. And so here you can see Rui, one of our students, wearing the VR display, and then the Jetson is sitting in the little backpack along with the battery, right? And during this scientific event, a public event where people public wants to learn about all the scientific research going on at the university could come. And so we had the person, I did do things like trying to stack up blocks, right, with the output from this phosphene display, or even to try and catch a rope swinging by to see, just to let them experience what it feels like, right, when you get such a visual input. And so just for fun, so here I'm going to show the phosphene output, and I'm going to ask you what you think you see. Okay. All right. So this is something that, imagine that this is what you would see. You have electrodes, and I'm trying to present something to you. Can anybody guess what that could be?
Somebody dancing.
No.
Snow in Switzerland.
It wouldn't go like this. Snow is good. Okay. Yeah, very good. Yeah, you see, if you look at it long enough, you could kind of guess. Yeah, and so just the actual DVS output. Yeah, so that's easy, right? Yeah, but with the phosphene output is way more difficult. Yeah. So anyway, I think it lets you appreciate what somebody, who's getting one of these prostheses would be seeing. Now, the next thing is we say, look, can that person play a game, right, with this kind of output? So here again, you try to guess what game it is. What is it? Yeah, it's a Pong game. Very good. It's a Pong game where, the ball bounces from one side to the other. Okay, and here's the DVS output. Yeah, so that's easier. You see the ball on one side. And basically the person is actually playing the game. It's actually moving the mouse to bounce the ball away from the walls. Okay, all right, so that's it. And so let me just end with this slide over here. So there are many next steps. And I think first is that we need to push all the stuff into an IC that implements the phosphene stimulation network and also combine with the IMAC basic. So with the probes, we're still doing experiments in mice and rats. And then DMH group has even more subjects coming in but they'll do it with the Utah array electrodes. And then our last bit is to be able to create a closed loop system, a closed loop setup or an experiment using the recordings to improve the stimulation patterns, something that we have to think about what kind of experiments would be good to do. And so, yeah, acknowledgements, so like to acknowledge all the members of the, Viper group. I mean, they're a great set of people to work with. Yeah, and it's nice to work with groups that are experts in different areas, right? And you get to learn also about different areas than just building your little ASIC and showing some simple applications. So I love it. And also, yeah, members of the census group, also the EU Horizon 2020 program for funding this project. And thanks for your attention. And if you have any questions, yes, we'll try to answer them.
A little over time, so
Yeah.
we're all here. That's good.
Actually, I was right in time because we were late with the
So,
getting that thing to work.
So, yeah. Okay, so questions?
Do you expect any issues with differences of how we can
Not at the moment because we're bypassing the whole retina stuff and going straight to the cortex. Yeah, so I think it's more of understanding when you stimulate at different places in the visual cortex, what's the picture that you see in front of you, and then you have to stimulate the electrodes correctly, if you like, so that you see an image if that's what you want that person to have. And so in the UMH experiments, they actually go through each electrode and stimulate the electrode with different levels of current so they can understand how strong the percept is and where is it located. And then once they have that, then they can create the proper output.
John.
Yeah.
Yeah, very nice talk.
Right, John.
Actually, I have one question about the electrode side. And this is not your material.
Yeah.
So when you implement the flexible electrode, you must get into the injected, so you use the shuttle, right?
Yeah.
The shuttle itself is rigid material. So when shuttle getting into the brain, it may induce the tissue damage, right?
Yeah, that is true. Yeah.
So that it happens in the glial cell and the exercise really comes again. And
Yeah.
will happen anyway.
Yeah,
So
that is true. Yeah, I think they tried.
We couldn't understand it.
Yeah, so he's saying that because you have to use the shuttle to insert the electrodes, you could also cause damage, right? When the shuttle has to go in and just to put the electrodes in. Yeah, so it's actually what they try to do is to make the shuttle a little bit higher up, if you like, right? So that they can push the electrodes in. So they don't like make it like 1-to-1, right? So you're right, there'll be some little damage that can happen, but they try to minimize it. Yeah. And then they make the shuttle actually very thin, like the silicon also extremely thin. It's tough when you try to insert flexible material into something that's equally flexible or mushy. It's tough.
So I think you mentioned that your stimulation chip could have 8 templates of different kind of pulse waveforms.
Yeah, 8 stimulation patterns. Yeah, so the stimulation ASIC from IMAC can have 8 stimulation patterns. So you can program 8 different types of stimulation patterns.
But do you have to switch them out for a different phosphene or image you want the participant to see?
No, because it's mapped to the electrode that you're stimulating, right? So once you know the level of current that you need and also what the pattern should look like, right? You just program it into one of the 8 units, and then you say this output is, going to be driven by that pattern. But you can only have 8 different patterns, for this station. Yes.
I'm curious if the patients report seeing any color.
No, there's no color. Actually, Eduardo Fernandez has great stories to tell about the subjects. In the second one with the man in the virtual reality room, it turns out if you stimulate the electrode, you don't see a dot. You can ask the person to draw what they think they see or what they are seeing actually. And he drew like a square. It wasn't a dot. And then they said, interesting. He drew it again and drew.
Can I see what they draw?
Yeah, and then another one, he drew like a funny ellipse. All right, so it could be if you put it in a higher level area, you're not going to see dots. Yeah. Yes.
How would you look to stimulate for depth perception?
What's the question?
Yeah, how would you stimulate to see depth, to perceive depth?
32 by 32.
Yeah, not going to. Yeah, I don't know. I don't think we can. yeah, we haven't thought about it that far yet. Yeah.
I think the answer is that you have a stereo vision system or a depth camera, and then you encode the depth into the phosphene directly. Right? So you can only light up phosphene if something is close enough.
Yeah.
I mean,
Yeah,
you
that's
do the
true.
depth perception, and you give them the answer. Right. Yeah.
That's true. Yeah. Yeah. Use a code. I think in the end you use codes rather than like an image like output.
So in the final video that you showed, people playing ping pong like that.
Pong. Yeah. Pong.
Pong. Sorry. So that person was a person who could see it before, or it was the product of training for people who couldn't see.
No. No. That one was just that you put the VR display on them and then you show them this phosphine output, this very coarse phosphine output, and you ask them to play the Pong game. They didn't get trained for it. But the fact that this ball was moving, they could get an idea of where the ball is and they moved the mouse.
When you say they can see, right? Normal people.
Yeah, but we put the VR display on them. So what they're seeing is just the phosphine map that I showed.
Sure, just like the video we see.
Yes, exactly.
Then that makes sense.
Yeah, right. I mean, it's definitely much better than what the real patients would see or will see. Yeah.
I think it's worth pointing out, Shih-Chii, that all this is very illusory, right? Because in reality, the people get an implant and they see the only phosphine they get is a little tiny patch that basically a few moons in diameter, right? In one half of the visual field currently. If you see a little patch of the visual field, it's not like they see the whole world now. They see a little patch.
Yeah.
Everything has to go into those 100, 10 by 10 pixel,
30 by 30.
Yeah.
10 by 10.
So, sorry, follow up. So you said that they see, but the follow up with the question that asked earlier by the man over there.
Yeah.
Is that how is it mapped? How I still don't understand how is it mapped? Like,
so so for every electrode they will stimulate it with some level of current, and then they ask the person, what do you see, right? So that person who's blind will say, okay, I see it kind of around there, I see it about this size, and then they stimulate the next electrode, or what do you see, or where is it? And then the person kind of draws it right on a little screen. So then they have an idea of how they should stimulate it, so that person sees what you want them to see, if you like.
Sketch the percept on a tablet.
It's like a mapping table that you have to create.
So is that like the common way that people always do, or the way that people said we perceive things as we grow up?
Yeah.
Is that we actually touch, right? Or would it be better that we provide the other sense for them to provide feedback other than talking, which is really slow?
Yeah, I mean, there are different kind of aids for people who are visually impaired, sometimes also with tactile or even with audio, right? The different sensors that you can use to help them, like to see the world. Yeah. Yeah, with this one, it's just like directly they see the light, right? But people can perceive even with like sounds, right? Some people actually, if they hear some kind of sound, they can imagine, oh, it's like this and stuff. Yeah.
It's kind of a follow-up to that point as well. I mean, do you see any change over time that people get better at it, like the longer the implant is in there? Because I would assume that maybe the circuit needs to reorganize a bit.
Training. We've asked this question. That's why they spend so much time with the patient. They have the 6 months and they bring them in every single day for, I don't know, they said it was like, I don't know, 18 hours.
So they rewire their cortex.
So they could be rewiring and retraining, just training them, right? Or giving them feedback, oh, you should have seen this. And so I think it's both, rewiring itself. But they only have 6 months, right? So it also depends on the age and also whether the patient lost the sight for a long time or short time. Actually, in the second patient was kind of amazing because he lost his sight, I think, for 2 years because it was an accident. And then when they implanted the electrodes, and suddenly he said, I can see. Like something very sort of coarse. But it turns out because somehow when they stimulated that part of the cortex, he somehow got partial sight back. But that's an accident, I think.
That means that there is no you training. That means that you use the plasticity of the brain. Right?
Yes,
and
that's correct.
That means that the circuit is not the original that uses the brain, probably.
Yeah.
Because you
you
training and then they change the circuit
Yeah, there's some rewiring. Yeah. I mean, it depends on the person too, right? How how long they've lost their sight, how young they are, etc. Right. So we can't say that it's like one thing with every patient that comes in. Yeah.
When I saw the current stimulation profile, I saw that your amplitude is somewhat low, 16 microampere and then 20 microampere something, right?
Yeah, 6 microamps. We want it to be low.
Oh, I see.
Yeah.
Typically, when I saw the papers, typical current stimulation amplitude is typically 100 microns or even more.
No.
Do you see any impact on the stimulation amplitude?
Yeah, so really they want to stay at very low currents, right? The fact that they can get something even at 5 to 6 microamps is a good thing, right? Because you're going to have thousands, huh?
Over what duration?
Oh, what duration? Yeah. Yeah, it was like 100 microseconds or so. Yeah. So
there's very little charge delivered.
Yeah, it's very low charge delivery. Because eventually, with the thousands of electrodes, right? Imagine you're stimulating a bunch of them at the same time, right? You don't want to have accumulation of charge. And they do see differences when you stimulate, say, a pair of electrodes versus one electrode at a time, right? So the threshold current drops if they're stimulating multiple electrodes. Right? Yes.
So related to the electrodes that you said, after you put it in for 55 days, if I remember correctly,
yes.
and the electrodes come out to look perfectly the same. So, but what?
Not perfectly the same. They'll never be. Yeah, it just not degrade like sufficient.
Yeah, it doesn't look degraded much.
Yeah.
So what would be the mechanism to make it degrade? Because I'm just wondering what mechanism that you try to avoid to make it longer.
Yeah. I mean, I presume that if you use very high currents, the material's gonna degrade faster, right? And maybe the reaction with the brain fluids. I think that's
glial scars.
Yeah, yeah, exactly. Or cells growing.
Glial scars.
Glial. Yes. Yeah. Right. Yes. Yeah. So nobody's. Yeah. So you have to really check to make sure the electrodes don't degrade over like a year's time, right? And there are other groups also, including a group in our institute, who's also developing this kind of electrodes, and they can show that it lasts over a year. But it's a long time of waiting, continuous stimulating.
So that will happen.
I mean, it did degrade in the mouse. After 55 weeks, the required current went up by a factor of 2 or something. That's only 55 weeks, right? That's
that's a year. That's a year. Yeah.
Mouse. That's a lifetime of a mouse.
Continuous stimulation, right? You don't continue stimulate.
1 year of vision is great.
Yeah, that's what they're doing.
So if you want to make it longer lifetime, do you rely on the material of the electrode, or you rely on the way that you put the electrodes in, or is that the way you put it?
It's
glial cells.
Yeah. So
any interactions in the brain.
I think yeah. I mean, it's really. I think it's a part of it is whether the electrode over time will cause cells around there to die, right? And that's what people are most worried about. Right, because if the electrode creates a problem, you see when you look at one of those pictures, those cross section, you see a dark area around the electrodes.
So I understand that part, but is that material would help it make it longer, or is that the way you put it in?
Yeah, I think right now people are concerned with the material and also the fact that these electrodes should be very small, right, so that they don't kill off cells. Yeah. It's the material in that, and then once that's established, then it's how you can insert them, because the smaller you make them, the tougher it is to get them in, right? So that's the challenge. Yeah.
And it's even open whether this is the right thing to do or whether optical stimulation is better. It's still open.
Yeah, there are many. Yeah, you can think of many other possibilities that should be explored. Yeah, not just this one. Yeah, but you can. The nice thing about this whole technology development is that you don't have to use it only for helping the visually disabled, right? As a prosthesis, you can use it in any neuroscience experiment. Just think of it like a bonus, right?
Because, yeah. Yes, Dr. Liu, there was a slide in the presentation that has a decoder.
Yes.
And you said it's not needed because. So I presume that decoder is modeling what's inside the brain. basically
Yeah.
the
It's a-
reconstruction process of
Yeah.
the patients.
You're talking about a variational autoencoder that we use to encode the input into the simulation pattern. Yeah, so you can kind of think of the decoder as a person's brain. Yeah.
But what I mean is different patients have different brains, obviously. Right?
Yeah.
So
and-
how do you design that decoder so that this is a golden standard to train your
Yes, this is something that some other groups are looking at, and actually you can look at the work of Michael Byler, who's had presented a couple of papers now at Neurips where you would train the decoder so that it's patient specific by just having an X-ray input, for example, right? Then you can change the decoder for the person. Yeah. I mean, it's a research area, and if you have some bright idea, you can also train some network to do this. Yeah, but it's really exciting, I think.
Thanks so much.
Yeah, thanks to all of you.